want to make this integration by parts intro video because when I was studying integration by parts, I got totally lost. And trying to figure it out, I learned an awful lot, and I want to share that. So it's easy to get lost in it because by the time you get this into calculus, it could all start looking like gobbledygook, and you're just numbers, and you're forgetting what you're doing, or at least I was. So I went back and revisited everything. And integration, as it turns out, the main stars of integration are squares and infinity. So we're counting squares, and we're counting how squares accumulate. And we think of that as area. Like, what's the area of this shape? It's 4 square units. But where do we look at them in calculus? Well, we're looking at them between the function line and the x-axis. This line describes a relationship, how things are changing in relationship to each other. And here are the squares, and these are the squares that we're counting. And calculus gives us a way to do it. Integration gives us a way to do it. We're used to area formulas, and that's basically what you're looking for in these. You're looking for what's a formula to help me find this area under this curve. And this curve is infinite. So it creates a little bit of a problem. It's also wiggly. It creates another problem. But like I said, we're used to area formulas. There's the formula for the circle. It's round. It's not giving us a hard time. We've got a nice little area formula. We've got the triangle. The point is, we're seeing area formulas all the time. And by the time we get to calculus and call them integrals, it's still area formulas that we're looking at. I want to start off with something really simple to look at. You may remember this for 3rd or 4th grade. You're finding the area of a rectangle. And we think of it as, we're taught that, the units have to match up. This is inches, this is inches. And this would be 4 times 3, length times width. So this would be 12 square inches. In calculus, you're thinking about it differently. You're not thinking about a thing. You're thinking about the area underneath this line. This is the line y equals 3. And it goes on infinitely in both directions. And it makes no sense to count to infinity because you'd always get the same answer. So we have to, the leap is to think about this differently. Instead of thinking about it as inches, we're thinking about an accumulation of squares. And instead of this being inches, the x-axis, this is the x-axis. We think about the x-axis as time. Because time is infinite. So there's the x-axis, and we want to find out how many squares are accumulating between the function line and the x-axis. Now these squares stand for something. It's not just really about counting squares. So if you're thinking of this as time, you can think about any unit of time. You can be thinking about this as months. Months in New York State, where rain is falling between August and October. And this could be inches. So after 1 month, you have 3 inches of rain. After 2 months, 2 inches. After 2 months, you've got 6 inches of rain have accumulated, and so on. But the thing is what we've done is we've created a boundary within infinity. And this is how we write it. We're going to be looking for the sum. So we do that beautiful big integral sign, the S sign, the sum sign. We're talking about y equals 3. That's how to describe this particular function. And we're looking at it between the function and this axis, dx, this axis. And the boundary we're talking about is going to be between, and for this one, is between 0 and 4. Now, my study of calculus has told me that the area formula for this function is 3x. And I'm not going to go into how I got that, but all of these formulas are right here in your calculus book. Okay, so what does that 3x mean? Well, actually you can graph that function and it looks like this. And this is the cool thing, that this function, which looks like this, becomes like a secret code book to tell you how many squares are in this or within this boundary you've created. So what I mean by that is that you can look, let's say this is a 1 hour mark. How much is accumulated after 1 hour? Let's say you're walking for 1 hour and these are miles. You can look on here, and where the 1 meets the line, you get a 3, and it tells you. So it tells you that there's 3 squares here. And you do that for each one. No matter where you end up on the intersection of this line, you can tell you can talk about at how much time has passed and how much is accumulated there. I don't know. I think that's amazing. So, I said this is going to be about integration by parts. But you have to understand what you're looking at in integration first. You're looking at there's infinity underneath here. You're creating a boundary around infinity. How audacious. So there are a lot of functions that we know the area formula for. Like, we know that the area formula for x squared is x to the third over 3. And again, it's just very cool. At 2 hours or 2 whatever, you can look on this function and see that you've accumulated 2.667 squares underneath the curve. There's other functions. There's just lots and lots of functions that have their own area formula. Here's another one. It's pretty easy to figure out the area formula. This cosine has its own area formula, and then you can figure it out from the 3x. But what doesn't have its own formulas is when we do something like multiply x squared times cosine 3x. That's what we need integration by parts for, because you end up with a function that looks like this, and you have to figure out an area formula for that. So that's all I'm going to talk about in this video. In my next video, we'll be just talking about how to do that. But the important thing for me is that there is this understanding of what these functions look like, what they look like once they're multiplied together, and what your answer you're getting. The answer you'll want from this one is maybe you're bounding it at 2. And there's a little tiny bit there. There's a negative amount here. There's a positive amount here. And it turns out that the accumulated squares is 0.075. You know what? Who cares? The cool thing about is how you get to that spot. So, to be continued.